Here we go live, and I'll start the recording also.
Okay, thank you so much, sir. Now I will going to start.
Just a minute, record the cloud. Yes, Kriti ma'am, we are ready to go now.
Okay, thank you so much, sir. So, hello everyone. I, Kriti Vishesh Jaiswal from Navrashna University, welcome you all to the fourth webinar organized by Navrashna University jointly with Binghamton University, USA. Today's webinar is about how electronic manufacturing industry can be benefited from the digital transformation using artificial intelligence and machine learning. So now I would like to invite Dr. Nilay Yajnik, Provost, Navrashna University, to shed some more light on today's event. Over to you, sir.
Thank you, Kriti. And on behalf of Navrachna University, I wish to welcome Professor Michael Testani from the Binghamton University, Thomas J. Watson School of Engineering. I also wish to welcome the speaker of today, Dr. Sang-Won Yoon, also from the Thomas J. Watson School of Engineering at Binghamton. Welcome to both of you to India virtually, and we really look forward to your session today. Navrachna University is a university which encourages and always encourages such cutting edge topics and such kind of discussions which are very relevant to the entire industry. And this is what we try and give to the society. This is what we try and give to the industry and to our students. So I'm so happy to see a very large number of participants, both students as well as professionals from across India and the world attending today. I too look forward to listening to Professor Sang-Won Yoon, especially on such an interesting and a very cutting edge topic like artificial intelligence and machine learning in the electronics industry manufacturing. Thank you so much.
Thank you, sir, for your inspiring thoughts on the program. So now I would like to request Mr. Michael V. Testani, Director of Industrial Outreach from Binghamton University, to introduce our guest speaker today.
Thank you so much, Professor Kriti. I'm delighted to be here. I have some slides to introduce today's speaker, but I want to extend, well, first of all, I want to wish everyone health, safety, and wellness in light of this current pandemic. So certainly my thoughts and prayers are with all of you. I do understand that things are leveling off and getting better, which I'm delighted to hear that there is some light that we're all seeing. So, first and foremost, my thoughts and prayers are out to you all. But I want to thank you all for having us here today. I want to thank Provost Yajnik, Professor Amarish, Professor Kriti, Professor Dinesh, of course, Vaibhav for his support with making this all happen. We wouldn't be here if it wasn't for the leadership there at Navrachna, and I'm very appreciative for that. And I just want to share a few slides about our organization, right, which is the Thomas J. Watson College of Engineering and Applied Science. I think there's a lot of synergy between our organization and your organization. So welcome to the event. Thank you all for joining. I want to thank the participants for being here. Right, we would not be here if it were not for you all. And as the provost rightly said, it's these emerging technologies that are of interest to all of us and can effectively change the world. So I think that's exciting that we can all have a hand in shaping the future. And in the Watson College, we are a world-class institution. We are dedicated, just like yourself, dedicated to quality higher education in engineering and applied science. And we have a very, very strong international perspective, right? It's that perspective that has brought this collaboration together. And I'm personally delighted for that. This is one of many series in this collaboration and a part of future collaborations. We're starting with these technical talks, and we'll expand other forms of collaborations and pathways and all that. So we look forward to that as well. I certainly want to acknowledge, right, all the officials who helped make this happen. I want to call out Dean Srihari, who is integral in forging this relationship as well. And certainly Dr. Amarish, Professor Kriti, Professor Dinesh, and certainly Provost Yajnik. So thank you all. And as was stated, this is the 4th of 7 technical talks. So this is very exciting. I am very interested in hearing from Dr. Yoon as well, because this is very relevant, where machine learning and artificial intelligence are being applied in a real world domain. And you'll hear about a few of those. Yeah, so this talk is entitled Digital Transformation Using Artificial Intelligence and Machine Learning, and focuses on electronics manufacturing. But I think you'll see some other applications from Dr. Yoon as well. So I'm delighted to be introducing today's speaker, Dr. Sang-Wan Yoon. He is a part of our System Science and Industrial Engineering department. He's been an outstanding faculty there for several years. You can see he was a recipient of our SUNY Chancellor Award for Excellence in Scholarship and Creative Activities. So we are part of 63 other institutions within the state of New York SUNY system. So that's a very prestigious recognition. And we're delighted for Dr. Yoon in that regard. And he has vast experience collaborating with industry. You can see some of the industries he's worked with here. And this is just a short list of a few, but he's worked with Toyota, for example, Raymond Corporation, which is a subsidiary of Toyota. I think you'll hear a little bit about that today. Analog Devices, Samsung, Sanmina, Xerox, Innovation Associates. In healthcare, United Health Services, Montefiore Medical Center. Distribution, Bennett Distribution Services, US Express, and the list goes on and on, right? So he's published, right, as a result of all these collaborations, he's published over 130 international renowned journals, conference proceedings. He's a member of our Binghamton University Data Science, Transdisciplinary Area of Excellence. He's an active member of our Health Sciences, Transdisciplinary Area of Excellence. So it's my honor and privilege to introduce today's speaker, Dr. Sang-Wan Yoon. So Sang-Wan, we will turn the floor over to you, and thank you so much for being here today. Excited to hear your talk.
Thank you very much. Oh, this is my honor, everybody. Can you see my screen, presenter view, and can you hear me okay?
Not yet.
Okay, not seeing the screen yet. Not seeing your screen as of yet.
Okay, so let me see. So, okay, let me share my screen here.
Yeah, it's
How
here.
about that?
There it is.
Here we go.
Perfect. Okay.
Perfect.
Hi, thank you everybody for having me. So today's talk is digital transformation using artificial intelligence and machine learning. And I'll probably talk about a couple of the manufacturing systems, but mainly I'd like to focus on the electronics manufacturing. Binghamton University is known as the kind of the hub of the electronics packaging and electronics manufacturing research. Because the Binghamton University, especially the Watson School, is founded by the IBM, Thomas J. Watson, a long time ago. So we have a lot of expertise in this domain. So this is a brief agenda for today's talk. So I'll probably go through the very, very high level. What is AI? What is Industry 4.0? It's my view. So what I see as an AI and what I see as an Industry 4.0. And after that, I'll talk about some Toyota and Raymond project, and which is a warehouse operation project. This one is relevant to the Industry 4.0 concept and something that we can learn from the warehouse operation toward the Industry 4.0 implementation, okay? And after that, I'll have a deep dive on the smart electronics manufacturing. Under that, I will cover 3 topics. Electronics manufacturing mainly has 3 phases, 3 main phases. The one is the stencil printing process, and second one is a mounter. A mounter is actually to print the components on the PCB board, and after that, we have to cook the mounter with the cook the PCB board with the components. So that's a reflow process. So I'm going to talk about all 3 areas, and then I'll end with the future work. So before we talk about the today's topic, so this is what I do. This is what I'm working on it. So I will say like I have a sort of the 4 pillars of my research domain: simulation-based research and collaborative control and coordination and large-scale systems optimization and analytics, data science and analytics type of research. And in the center, I list out the sum of my funding sponsors. Okay, so collaborative control and coordination is my PhD topic. It's a very theoretical topic. So today I'm not going to talk about this one, but instead I'll probably cover the other 3 topics in today's talk. Okay. So moving on. So this is the big eye chart about the IoT and AI. So let's look at the chart on the right. So if you look at the chart on the right, so Industry 4.0 is some of the buzzword that everybody's talking about these days. So in order to realize the Industry 4.0, so you need to have many other tools and methodology that you have to integrate them together. In Internet of Things, basically it's a sensing technology. A lot of sensing technology is needed, and simulation and robotics and augmented reality, virtual reality, and then big data and all that. And also the cybersecurity is one of the big issue and whatnot. But if you're looking at the entire the methodology, one biggest part is the data. So we have to utilize the data-driven approach. So once we have a large scale of data, and the next step is how to analyze the large scale data. When you have enough amount of data, it's easy to apply the AI and machine learning techniques. So in order to realize the Industry 4.0, my viewpoint is AI is sort of the backbone of the Industry 4.0, okay? Because we are living in a data-rich era, and we can develop so many different things with the AI and machine learning, okay? So AI and machine learning and Industry 4.0 become very, very popular these days. The question is, why now? Why 10 years ago? Why 20 years ago? So why everybody talking about AI and machine learning now? So I'll take you to the chart on the right. So if you're looking at this chart, there are some interesting things happening over past 1 or 2 decades. For example, cost of the data handling. So compared to the 2004 and 2014, and cost of the data handling reduced the almost 98%. Okay, so which means that data handling become very, 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 very cheap. Okay, and cost of the bandwidth. So this is how fast we can transmit the data, and many of the countries are moving to the 5G, and they're applying the 5G concept even in the manufacturing side. So speed of the data become faster. Okay, and then also if you look at the hardware and mobile devices, we have a lot of mobile devices, we have a lot of sensors, and we also have a lot of hardwares, and hardware performance is getting better every year. I mean, it feels like every day that it's getting better. So the maturity of the big data, even within the kind of the 5 years, and it's doubling up. It's doubling up. So this is kind of the backbone of why the AI and Industry 4.0 become better. So everything is a data-related one, and all the hardware, all these things are getting better and better and cheaper and cheaper. Okay. So this is a very, very high level of the history of the AI and machine learning. So AI was introduced. Let's put it this way: AI was introduced in the 1950s. Okay, and a group of researchers are getting together in some of the conference, and they, kind of talk about how to make the machine and human intelligent. Okay, how to make a machine and a human think like human. So probably this is a kind of the genesis of the artificial intelligence. Okay, and then after that, moving toward around 1980s, and people will start discussing how to make the machine or the software and algorithm learn like a human. So human make a lot of mistake, when we are young, and everybody make a lot of mistake, but we learn from the mistake, and then we start developing our own knowledge, and then making less mistake, and then become mature and getting better and better. So this is a kind of the concept of the machine learning. But if you look at the 1980 and 1990, that time, even though the artificial intelligence, machine learning, a a lot of the machine learning algorithm that we are using was introduced back then, but AI was a little hot, but it's not like really hot like these days because of the hardware performance issues and a lot of issues, and also the problem that AI and machine learning can address was relatively small compared to the problem that we're solving now. And around 2010 or the little before the 2010, deep learning was introduced. So basically, deep learning is based on the neural network concept. So if you develop the very sophisticated neural network, and issue was computation, so it requires a lot of the computation iterations and whatnot. Because of the recent like GPU machine and all kinds of devices, and then people talk about the quantum computing in the future, and all those things are kind of the solve the computational power and issue, and the data become rich, and then the data transmission and all the network devices getting better. So this is kind of the moment that we can solve a lot of problems using AI and machine learning. Okay, so this is kind of the very high level and simple summary of the where AI is coming from and where we're heading. One of the problem that you should be aware, so under the deep learning, this is another scholarly discussion and everybody's having it, why the AI method works better than the other classical or traditional method, and how to explain the why this method works better than the other one. This is kind of the big kind of question that everybody's trying to address these days. Okay. So this is also another eye chart. So if you look at some Industry 4.0 and AI research statistic, I want you to look at these charts. If you look at the red and blue line, so blue line is indicating the number of the AI paper published, between 1998 to 2017 from US. That's the blue line. Okay, if you look at the red line, so this is the number of paper from China. So interestingly, about 2005 and 6 and that time frame, and number of paper published from the China exceed the number of paper that the US is publishing. So if you look at a little bit of history of AI, and a lot of the Chinese scholars and working on the AI, there's a lot of publications coming out of the AI, and China is doing some great work. Like if you look at some of their industries and whatnot, they're catching up, and some other areas that they're actually competing, like some other the advanced or the developed countries, the industry sectors and whatnot. So that's what they are doing it. So, but overall, if you look at the entire chart, like the number of publication in the AI is increasing over time, right? So probably it's 2 to 3 times over in last decade or two. So this trend will be seen in near futures as well. So this is the kind of the time that we have to pay attention to this one. So in terms of the number of robotic install, and there are a lot of companies and countries and investing money on the robotic system, and South Korea, 710 robotics per the 10,000 employees. And so a lot of companies investing money and effort on the robotics. And then also the R&D money is a lot, like if you look at all these names and whatnot. So this is a kind of time that a lot of people are combining robotic and then AI and then machine learning and everything together in order to be the leader of the future industry. So AI is not, AI becomes the sort of the must-have item for us to consider, okay? So now let's look at the warehouse application examples. Several years ago, I received some funding from the Toyota Material Handling. Toyota Material Handling is different from, Toyota automobile sector. So this is a material handling division, and then they are making kind of the lift truck like this. And then the Raymond is a sister company of the Toyota Material Handling. Okay, so they are sort of the same company. Okay, so if you look at this warehouse, probably you will see the future of the manufacturing and the warehousing. So this is a warehouse and you have lift truck and you have everything in this figure, right? Lift truck and then the racks and then automated storage system and all that. Even like this green thing that you're seeing it. So that's actually the wireless charging system. So that's what you're seeing. But you can see everything, but only thing that you cannot see from inside the warehouse in this figure is human. So that's kind of the future of the the manufacturing. So we are trying to remove the human being out of the warehouse, but instead we want to put the human being in the control system. Okay, so that the people do not have to go to the factory or the warehousing, but they can still control the system remotely. So having said that, so what is the most essential technology that you need to have? Probably the real-time location system. So RTLS tech, probably the beginning of the system, because we need to locate the lift truck, where this lift truck is located and which item that this lift truck has to pick up, and we need to know the location of that thing. Okay, so that's the thing. But if you look at the warehouse, this warehouse will be much more complicated than the outdoor the navigation system, because outdoor navigation system has a satellite signal, and then we can use the satellite signal and then find out where this vehicle is located or not. But this is indoor. Indoor means that we have more objects, okay, and then we have several options, but still like there's some problem with the real-time location. So that's kind of the system that we have to use it, and then also getting the real-time data and also to process it and then control it. So that's sort of the way that we have to do. Okay. So evolution of the warehousing operation. So there's a manual and semi-automated and then fully automated warehousing system. So if you look at the most of the company, they are in between the semi-automated and manual. I think most of the companies are located in that area. And then a lot of companies try to move to the fully automated warehousing operation. So most of the companies in between here, and then they are moving to this direction, for example. But if you are going to the Amazon warehouse, which I've been to, and they are not even in the fully automated warehousing operations, still like they are in the semi-automated. So some companies may be toward here, and some companies may be toward here, okay? So that's what they're doing it. So there's a lot of automated unmanned lift truck or the vehicle system that the people are talking, and then they're trying to develop. Okay, and then if you see here, and the real-time location information system is one of the essential systems that we have to use it. And there's also the IoT system that we have to use it. Okay, so that's kind of the evolution of the warehousing system. So if you look at the manufacturing system will follow the same sort of structure, starting from the manual and semi, and then the fully automated. Okay, so that's where we are, and I like to point out the some of the important things that we have discovered when we are working on the this warehouse system. So we discover and this particular warehouse system and using 9 or 10 different like a computing system. So when you're looking at the 9 or 10 different warehousing systems, so time clock, okay, time clock on the different computing system has a some differences, okay. So and then I'll explain why this is important. Okay, when you're using the when you're looking at your phone time and the watch, and then if you look at the computer time clock, there might be some few second differences and then tens of second differences, okay? So maybe like there might not be the real problem when we are using those clock and watch and the real-time activities, but when we are trying to do the some real-time control system in the manufacturing system, and this can be the one of the significant issue, okay? So let me give you some example. So there's we actually place the real-time location tag in the lift truck, okay? And then we've been collecting the real-time location information, okay? And after that, so if you look at the all these dots, so that dot is indicating that the lift truck is hitting some object. So because the lift truck has some kind of sensor, we are gathering that information from the lift truck. It seems like this lift truck is hitting some object, okay? And then we record it, okay? But because this particular warehouse using the 9 to 10 computing system, there are time differences, okay? For example, there is the this EST and the GMT time difference. So this is 4 hours. So this is sort of the easy to fix, okay? But even though we are using the real-time location tag, and we actually place the real-time location tag on the same vehicle, same lift truck, but the time differences between these tags is up to 2 seconds, okay? And then because of the other warehouse management system or the other system has some time lag, so come together, it becomes a 2 to 3 minute differences. Combining all these 9 to 10 computing system, okay? So having said that, so the RTLS system plus 2 minutes and the minus 2 minutes, it means your impact location can be everywhere, okay? Everywhere. So if you look at this chart, so we roll out the time clock and 2 minutes back and 2 minutes forward. So this is what you have. So this is kind of the big warehouse, but the impact can be the one corner of the warehouse and the other corner of the warehouse. Okay, this is completely different. So this is something that we have to address. Okay, now let me show you some of the simulation modeling and 3D modeling. Because when you get to the future of the Industry 4.0, and we are going to control the system remotely, then this kind of the simulation system become essential, because we cannot actually monitor the system with a live feeding. Then probably having this kind of simulation model and developing the machine emulator or the system emulator can actually control the system better. So this particular system is existing in the Giant Eagle, and I believe it's in the Pittsburgh. Okay. So we actually developed the simulation model. Right now, the simulation model is for just the throughput analysis and process analysis and whatnot. But in the future, if we have this kind of the 3D simulation model, and then we can just control it, okay? I'm looking at the entire conveyor belt. I can zoom in and out, and I can look at, oh, maybe like some of the machine has a problem. Okay, let's control it. Hey, this machine, you need to have some kind of the preventive maintenance and whatnot. Also like, oh, okay, so there's some kind of the resource savages and up there, and then, okay, maybe we have to send out the something, okay? So this is some of the system that we can consider. And we were able to link to the virtual reality system, and then our research team is interested in applying the augmented reality system in this, okay? So let me show you what we are doing. So if you look at this, give me 1 second. If you look at this robotic is a correlation robot. So it can, this is actually the application of the pharmacy solution. You can put the 5 different vials or bottles of the medication, and it can consolidate and put it in the totes, okay? So this particular system has been simulated in the simulation modeling. And then operation-wise, that this machine looks same, and also the operated same way. There are, I believe, the 53 tube, and then it's it can control it. Another thing that I want to show you is this is a robotic dispensing system. It's a octagon chamber, and then in that we have a Fanuc robot system, and then this system can take the vials and medication from the 80 different dispenser and place in the some conveyor belt and then labeling and then exit out. So I just want to show you that this is how we can simulate it, okay? So that this robot can move, so it's not randomly moving. So we have a program so that this robot is moving based on which medication is ready to pick up and then operate it, okay? So this is a kind of the level of the simulation model that we are doing it. And then now I'd like to show you I'd like to show you the Apollo Phoenix system, the bigger picture of this simulation model. So if you're just running this simulation model without the GPU machine, you can easily take more than like 8 hours and 10 hours and whatnot. I'm talking about only one runs, because this particular system can do the 100,000 prescription per 8-hour shift, and we can run it the 8-hour shift. But it takes quite a long time because of the very detail of the simulation that we are doing it, and we're collecting a lot of information. If you look at the correlation robot behind the back, so there's a dashboard, so we can actually collect the information, utilization information. So we are embedding. So not only the simulating, we are collecting a lot of data out of this one, so that we can analyze the a lot of system, a lot of things of this system. This is a linear dispensing unit, and again, this one is also doesn't exist in the simulation model. So our research team has to develop the inside the simulation model. So this is a back end of system. This is a packing station. By the way, we put the circle underneath the human being so that we can capture whether all the people can be the socially distanced. Okay, so that was a kind of the main idea of the putting a circle. So there's a semi-auto and a manual auto pack station, and then all this packaging will be packed out and then go to the sortation system. So if you look at the behind the this system, there's a sortation system. Now you're seeing it. And this system is a Eurosort. This particular system also doesn't exist in the simulation. It's the European company, and they're making this kind of sortation system. And we had to evaluate the performance of this sortation system. So we actually built it. And underneath, and then they drop the boxes, and then when box become the full, and then we have to take it to the truck, and then truck goes out. I'm not sure whether this particular system or this kind of system exists in India. So US, and this is one of the popular way that we prescribe, we actually get to prescribe the medication. So if you go to the pharmacy or the doctor's office, and sometimes they send the prescription information to this essential location, and you can get the medication within 24 hours. And that was a central field pharmacy concept. Okay, I hope that you got some idea about what kind of the 3D simulation model that we are doing it and that we can do. Okay, now, so let's move to the our main topic, so which is Industry 4.0, smart electronics manufacturing. About 2004 and 2005, we are getting into this domain. So we have actually entire PCB assembly line. We recently got the new reflow oven from Heller. Heller is one of the popular, actually the major player in the reflow oven. So let me explain this line. So we have a printer, soda paste printer, okay, and then the soda paste inspection machine. So this is inspection machine, and after that mounter, and then automated optical inspection machine, and reflow oven, and another AY machine. So if you go to any of the PCB assembly line, and this is what it looks like. If you go to the Apple PCB assembly line, if you go to the Samsung assembly line, so basically this is the main thing. Sometimes you need to have more than several mounters, but basically this is the kind of the line. Okay, so we on our campus we have an entire line. I believe this entire line is probably between $2 to $3 million. Okay. So we do have a 2 printer and then 2 mounter, and we have a 3 inspection machine. Okay, and then we have a lot of partners working on this research. Okay, so main idea is this one. So there's a soda paste printer. So this is a machine. Okay, so there are certain parameters that we can control. Okay, and then the SPI machine, which is the inspection machine, will collect a lot of data, massive amount of data. Okay, now once we collect the data, and we can detect any kind of problem from the printer. Okay, then the question is, can we connect this machine, printer and then inspection machine, machine-to-machine communication? By setting up that machine-to-machine communication, can we control the printer from the inspection machine? So this is a machine-to-machine communication. We have a lot of research result out of this. And then we actually extend it to the mounter. Same thing. So SPI and AY machine information together, can we control the mounter? Reflow is we just start working on this one probably just 8 months and 9 months and whatnot. Okay, if we are able to control everything 1-to-1, 1-to-1, 2-to-1, that kind of the combination, then we can realize the entire system can be controlling without going to the other facility. Okay, so that's kind of the high level view, and then I'll talk about the more detailed stuff. Okay, and then we've been actually printed more than 8,000 PCB board, and recently we made another purchase of the PCB board. So we are collecting a large amount of the data in this domain. Okay, so now, so this is a sort of the different PCB board and solder paste and stencil and then all that. So this is kind of the idea. So we have several PCB board from the ECRA JBO, and then we actually developed our own PCB board for the testing purpose. Okay. So now, so let's talk. I'm going to talk about the 3 topics: printing, mounting, and then reflow oven. So first up is printing. So stencil printing. There are many printing factors. Okay, from the stencil, solder paste, and machine level and whatnot. Most of the things are sort of the given or predetermined. Okay, so we cannot have like online control. So we are thinking that we can control only this setup. When you print the solder paste, then there's a squeeze blade pressure speed and some of the separation speed and whatnot. So those are the things that we can control. Okay. So now, so this is a more detailed illustration of the closed loop feedback control. So we are trying to develop the closed loop in here, printer and then SPI machine. Okay. So we are trying to use the AI machine learning method and because we're collecting a lot of data. So if you're looking at where are the data, so all the input parameters and whatnot, it's in the job file. Job file will be shared by the different machine. So SPI machine will collect the inspection result, then using inspection result, and then input result, and we know, okay, things are going wrong. Okay, then we can actually take action and analyze it. So AI and machine learning modules and algorithms are plugged into the SPI machine. So technically, we place another like sort of the mini GPU machine inside the SPI machine. Then we can calculate it while in the production, and we can do the control. So that's why this is a closed loop feedback control. There are 3 elements. So before the production, and we like to find out what are the optimal parameters. That's actually the pre-production, and we call it PAM. And then during the production, this is online control, and we're calling online POM. So printer online module or the online module. Okay. And then even if we have online and offline module, and if we do not have a good data, so I think everybody will know that the garbage in and garbage out. So if we have a not so good data, and the result will not be good, so we have to be careful with that. Okay, so this is what we are having it. So we are creating the closed loop feedback control, and then we are going to apply the same concept to the mounter and reflow oven. Okay, and then having that, we are going to improve the a lot of the process metrics and process parameters, and improve the throughput. And also ultimately that we want to improve the quality of the product or the PCB board that we are assembling in this line, and then increase the efficiency. Okay. So I probably mentioned about the PAM, POM, and PDM. So this is sort of the concept, and then we're developing this closed loop feedback control between the printer and SPI machine. And if there's a lot of the deviation from the one product to the other product, and then having this kind of system, and then we're gonna have a narrow deviation. So product will be, or process will be much in control. So that's sort of the things that we are trying to do, so that we can increase the reliability, and then system will be consistent, and we can eliminate a lot of the defects. When you have a defect, you have to stop the line and then study the root cause of the problem, right? So because we're removing the defect, and then line will be up and running longer period of time. So that's why we can improve the throughput or the yield. So, and then also if typically we have to place the couple of people, a couple of technicians to monitor each equipment and whatnot. if there's no defect and and whatnot, we do not have to place a lot of the technician over in this line. Maybe one technician can control the multiple line, so that we can minimize the number of people in the electronics manufacturing site. Okay, so that's kind of the idea that we have. So this is a result. Let me explain this result. So customer's best known result is the printer expert. Okay, when printer expert received the new PCB board and he has to study, and typically they're using trial and error method. Okay, you try some of the pressure and speed method, and then if things are not going on, and then they're changing. Okay, and then discover the best setting that you can have. How long does it take? It can take 1 week, because this is try and error. So you collect the data, and after that you have to analyze the data, and then change the setting, and then test it again and again. Okay, so this is taking can be like 3 days to 1 week and whatnot. Okay. So suggested by the PEM. So this is an offline control. Before we go to the production, we want to find out what are the best settings. So these are the settings that we discover. So the numbers are slightly different, as you can see. Okay, but in terms of the time, how long does it take? Entire process, beginning to the end, it could take only 3 hours. So within 3 hours, we can generate this kind of the setting. But now the question is, which setting is better than the other? Okay. So if you look at this matrix, this chart, and then PEM result from the other manufacturers has the CPK as 1.1, and we are improving the CPK as a 1.73. So if the CPK value is over 1.3, and then production is very much in control, so we were able to improve the 53% of the CPK matrix. From the one manufacturer to the other manufacturer. So 53 on the 30% of the CPK improvement. So which means the line or the production line becomes much more controlled by using AI-based setting. Okay, so actually this setting is coming from the actual automotive a PCB board. If you look at the vehicle, there's a lot of the PCB board that we are using it. Okay, and then this result is coming from that. Okay, now let me take you to the online control. So this is also the eye chart. So if you look at this bar, so this is a pre-production, and this is during the production. During the production, the nice things about during the production is we are gathering the more data. So because we are gathering the more data, and then we can actually improve the AI and machine learning solution. So that's why the CPK goes up. Okay, so we can keep on increasing. And in order to improve the CPK, we need to change the printer setting. But do we want to change the printer setting every time we discover the new setting? Probably not. Then we have to make so many changes, and then we're not sure that the production line will become the steady state. Okay, so that's why we build the simulation model. So this is sort of the simulation model based on the filtered data and the noise factor, and then we developed this kind of simulation model. So while the line, PCB assembly line is up and running, and we can use this simulation model and test, hey, optimal solution is changing. Is this a time that we have to make changes, or we should wait? If the setting is not much different, okay, we can keep going. But if the setting is completely different, and we have to move to another setting. So this is the kind of the ideas that we are using incremental learning. I just want to use incremental learning and then local guided search method, so that we have some kind of human expert ideas and knowledge-based system, and then develop some kind of the guided search method, because we want to discover the more area, some place that we never visit. So this is kind of the main idea of this one. In essence, we like to increase the CPK value from offline control to the online control. Okay. Now, so this is a diagnostic module that a couple of examples of the diagnostic module. So there's an abnormality detection and cleaning cycle. And so cleaning, I'll talk about combine them together, cleaning cycle and profile study together in the later slide. So abnormality detection, if we are collecting the data, if we know that something is going wrong, then if we detect it sooner and we can fix this problem, right? So that's kind of the idea. And cleaning is because this is a stencil printer, and the bottom of the stencil, every once in a while, we have to clean. There are two types of cleaning, wet and dry. So how often that we have to clean it, and what are the cleaning method that we have to use it? If we don't know this cleaning cycle and then profile, and technician has to interfere to the line, okay? So this is another, actually the current study is located in this domain. So now abnormality detection, so we are using the image file, and then we are using exception network. It's one of the deep learning method. And based on the different classes, 9 different root causes and then 6 different root causes, and we are achieving like around 82 and then 86% of the accuracy. If you have technician and technicians are trying to discover these root causes, a lot of technicians cannot find the root causes. So having this AI-based root cause analysis and abnormality detection is good. And also another thing is this is actually the 9 classes, the 6 classes. If the number of classes is only 2, like okay, abnormal or the normal, the accuracy level is become great and high. So this is actually a great study. One of the problems that we have is data itself is a sample data. We're unbalanced data. So we have a lot of good data, but we don't have a lot of error data. But once this module is implemented in the line, and then we start collecting a lot of abnormal data, and then the machine learning system will be much more intelligent. So that's our idea. So in terms of the cleaning, so this is what's happening. So you have a PCB board, okay? You have stencil, and you put the solder paste, and then print it, and then snap off. And then you have solder left on the PCB board, and there's some kind of the remaining part. Some of the remaining part can actually go to the bottom of the stencil. So as you can see, the bottom of the stencil, it looks like this way, okay? There's a lot of residual that you can see it. So every once in a while, we have to clean up. Otherwise, that leftover in the bottom of the stencil will be coming to the other side of the PCB board, and it can create some kind of the problem, right? So we have to clean. But next question is, can we use this residual information, bottom of the stencil residual information into the picture? So that was a question. So a couple of the printer machine does have a camera function, and we can take a photo and analyze the amount of the residual that we have. But it takes time, okay? Let's say the printing cycle is 20 seconds, but getting camera images and then process it, it may take 1 minute, for example. So it's not practical. We took a photo of the bottom of stencil every time, okay? So the main idea is, can we predict? So based on all the conditions that we have, some of the data that we can collect from the SPI machine, if we can predict the bottom of the stencil residual, things are much easier. So we built the simulation model, and by the way, this study has been published. So using the LSTM method, and we are able to predict the bottom of the stencil printing result. So there's a different shape of the aperture, and based on the different angle of the aperture, and we're expecting the different amount of the residuals. I think a rectangular one has the more residuals. And so we actually collect the data. A student actually put the camera underneath the stencil and took a photo, and then we collect the data and then we test it out. So and then result is actually very, very promising. So now this residual builder prediction model become input to the cleaning cycle and cleaning profile study. Okay, cleaning cycle. So if you can picture the production line, so you have PCB board and then printing, and then this PCB board has to go to the inspection machine. So think about this way. So there's a printer and there's a inspection machine. Once the PCB board come to the inspection machine and inspect it, while the inspecting is done, the other PCB board will be on the printer. So printer cannot wait, the inspection result is out, and then we have another updated printer setting and receipt. So the idea is we cannot control the one board after, we have to control the 2 board. because of the process. One board is in the inspection machine, the other board is already in the printer. So we cannot control it, so we have to predict the one board after. So this chart is illustrating this one. So we sort of achieved the very good result based on the gradient boosting method here. So now profile. So profile means that there's a wet profile and then there's a dry profile. So wet means if you use some kind of solvent and then clean up, so you can clean it better, but it requires a more dry time. So when you do the wet cleaning and you have to put the other combination, wet, dry, and vacuum, and combination of this one. So the wet cleaning requires more time. Again, this is a manufacturing and production line, so we try to minimize the entire time, right? So wet cleaning is something that we do not want to have it very frequently. And then dry cleaning is something that we can do it, but it takes a less amount of time than the wet cleaning. So what we did is we actually create the info file like this, and then we create the sort of the image stacking, okay, image stacking approaches, and then develop some kind of the machine learning algorithm and whatnot, and then decided, okay, so the wet cleaning is better, and then dry cleaning is better, and then what type of the study that we have to do. So after we build this image file doesn't exist from the SPI machine, so we have to create the new one, okay? And then having this cleaning profile selections, and we apply for the JBL board, JBL test board, and then this is a adaptive profile, and then this is industry standard. Industry standard as a default, let's say every 5 board, and then you have dry cleaning. Every 15 board, and you have wet cleaning. So it's a fixed deterministic cleaning cycle. The adaptive profile selection is based on the data that we have, and we are changing it. Hey, this time we have to do the dry cleaning, and then this time we have to do the wet cleaning, and something like that. So that's what we've been doing it, and CPK has been improved, substantially from the without the adaptive profile and then with adaptive profile selection. Okay. So now let's move to the Bounter study. Bounter study has the more data, for example, SPI information, like a soda paste volume information, and then the final location information with the AOI. So we kind of use the 2 AOI because the component will be placed over the soda paste, and then final location of the component has to be known. So this is what it is, okay? So you have MOM and MDM. It's the same concept. Also, another thing that you should know is what kind of the parameter that we can control. So this is the placement. This is placement, component placement operation. So where to put your component is essential. So the main thing is offset of the center, offset from the center. So is it okay to put the component a little bit off, controlled offset? Then there's a self-alignment. Self-alignment concept, let me explain the self-alignment concept like briefly. Even though you put your components over the soda paste is a little bit liquid. And when it goes to the oven and it becomes solidified, okay? It becomes rigid. And then while doing this chemical process, and then there's some kind of movement. And the entire business is coming from the self-alignment. This soda paste is coming to the center, and then also the component will be mounted, desired location. That was a concept. So there's some kind of movement that we can predict. We can predict, and by knowing that, and then where we can actually put the placement, then we'll have a optimal self-alignment outcome. So that's kind of the main concept of this study. Let me take you to this slide. This is, I think this one slide can explain, several other slides that I'm about to explain. So if you look at the yellow, this is a pad, and then gray is the paste, soda paste. Soda paste has to be over pad. So if in a perfect world, and then it has to be over exactly on the yellow pad, okay? But it's not. Like when you do the actual printing, and there's a slightly up. So typically, component will be placed on the pad, center of the yellow box here. Okay, this is the chip mounter or the placement machine default setting. Okay, and this is a Panasonic's the patterns idea. Okay, looks like a component is moving, but if you place on the pad, then because of the movement, you will never end up in the center of the pad. So why don't we put the components on the paste? So this is a Panasonic pattern. So you can actually search for it. This is actually the public information. So they have this method. Our idea is maybe it's not on the pad, it's not on the paste, maybe in between. There are some kind of the data and features and attributes that we can collect. And if we place the component in between, then final self-alignment result will be center of the pad. So that's kind of our idea. So this is our idea, okay? So having said that, we try to prove it. So if you look at this one, this two chart is the indicating where we put them, and then based on the different size of the component. And this is the final result that we're seeing it. So if you place on the pad, so you see the lot of the red. And green means it's if you place on the paste. And blue means you place on the in between. Okay? And then when you get to the final outcome, and you can see the green comes together to the center. And red become here, and then green become here. You can see. So we are kind of proving that, okay, maybe like in between, we don't know exact location yet, but if we are placing a component in between, and the final outcome will be moved to the center. So that's kind of the main idea. And you can see, so this is a different type of example. So, and then it will move to the other different location, okay? Something like that. And then also there is a surface evolver, which is the physical property based the model. And we are discovering, some of the inconsistency between the experimental result and then this solution method. And we're trying to improve the this surface evolver method based on the data-driven method. Okay, so we like to compensate the error coming from the surface evolver, because the surface evolvers are using the physical property, and the physical property may not be able to explain all the uncertain parameters and then conditions and situation. So we are in the process of developing the machine learning based method. Okay. So this is the idea. So we are trying to do the closed loop feedback control. Again, same concept as the mounter study, printer study, and then we are applying to the mounter study. Okay, so we identify the proper options based on the given SPI, so which is a printing result, and then we are trying to predict the post reflow, meaning after all the self-alignment is done, using the machine learning algorithm, and then find the optimal solution. So that's sort of the similar concept as the printer side of the study. So let me take you to this figure. So outcome MOM, online control. So this is the zero deviation from the center. So we are increasing from default setting to the MOM about 30%. So more components coming to the center end up being center compared to the default setting. So that's what we are seeing it. Okay. And then in terms of the diagnostic module, in terms of the mounter, there are a few things that we can study. So, we are collecting the data, and then after that, we like to see what kind of diagnostic module that we can develop. So there are three things that we are working on it. I think we actually complete this study, and we're looking at something else now. So there's an incorrect nozzle size. If the technician is changing the nozzle, so all this pick and place machine is based on the vacuum. So if you see the nozzle and then has a different size of the vacuum devices. So if the component is big, so you need to have a more bigger, like a vacuum area. And then if you have a small sizes, you have the smaller. So correctly, and then most of the component has the optimal nozzle size that you have to use it. But in the production, and human can make a mistake, or some of the nozzle, exact nozzle is not available, and technicians tend to use the one size up and one side down. Okay. when you are trying to buy some clothes and then you don't have an exact size, and sometimes you buy the one size up and down, like same concept, okay? In the pickup position, this is actually a component. We want to actually pick up the component from the center of the component, but sometimes it's not possible. Sometimes we are picking up the component a little bit toward the corner or the side, some rotation and whatnot. So this will affect the final positioning and then the contamination issue. Okay. So in summary, we developed this one. So individually, nozzle size and pickup position and contamination. So we have actually very accurate result. But if we combine the multiple combination, so contamination plus pickup, or the pickup plus nozzle. So if the problem become more complicated, and overall accuracy is currently around 95% and whatnot. Okay. And then let's get to the reflow oven. I will quickly go through this one because this is the most recent study. So reflow oven works like this way. So this is a reflow oven. So there are different temperature zone, 1 to 6. I think the one that we got have maybe more than 6 zone, but this is actually the old oven that we've been using. So that different temperature. So you can see the different. This is Celsius, by the way. By using this kind of the setting, and then all the PCB board component joint, so the joint has to follow this thermal profile. So this is kind of the line, okay? So, but each joint, we can set up only the one temperature, okay? I was told that the industry, some sophisticated reflow oven can have 12 different temperature zone, so which can have easily follow this thermal profile. So let's say this is thermal profile, and this is thermal recipe. The control that we can do is the thermal recipe and also the conveyor belt speed. So there are two things that we can control: conveyor belt speed and the thermal recipe. So far, we are working on how to set up the thermal recipe so that the PCB board temperature, when it goes to the reflow oven, will follow the exact thermal profile. So that's kind of the main idea we have. Okay. So this is experiments that we are doing. So we are placing the thermocouples over the PCB board and then put them in the oven, and then we are collecting the data. Our idea is that we are trying to use the heat transfer equation and plus data, because the reason that we are using the heat transfer equation is to try to minimize the number of data collection. So having said that, so we collect the data, and then after that we are trying to develop the prediction model of how the reflow oven works, and then we're trying to optimize the reflow oven to the true board temperature. So right now we have done like a couple of the data collection. One is on the joints or the PCB board, or the little above the PCB board. So if we have some of the IoT devices, and whether we can actually predict the actual joint temperature. So based on the result that we got, so we are kind of getting about 95% of the accuracy at the moment. I think this is a kind of excellent result. And then we are using the prediction model, and after that we solve this prediction model based on the evolutionary strategy method within 10 iteration, and we are able to get the thermal recipe. So how long does it take? And typically in the industry, our method, entire process will take about 20 minutes and 30 minutes and whatnot. In industry, if your reflow oven is not working, that you have to shut down the entire line. So this is actually the huge, okay? Then how long does it take to reset? Probably it's 3 hours to 6 hours and whatnot. So at least 1 day, okay? At least the entire day can be gone if your reflow is not working. But in our study, and then getting the data and then setting up the new parameters and whatnot, it will take about 30 minutes or so, okay? Only because the technician has to do the trial error type of method. So this is kind of the temperature we are getting it. So some of the temperature that we know, okay, this is a kind of the best temperature we know, and then the AI based temperature, gap between these two is actually around 2 Celsius degree differences. Okay. So in the future, what we are trying to do. So right now, I walked through the SPI machine and printer side of the feedback control. and mounter to the AOI machine feedback control and leaf-flow oven, and then this feedback control. And after we configured all these things together, and we like to put the high performance computing and then put the data in the cloud system so that we can actually control the entire system without physically going to the this line. Okay, so we call it, this is an integrated platform for the smart electronics manufacturing. There are many things that we have to work on it. There's a cyber security issue. If you remember my Industry 4.0 AI slide in the beginning, so cyber security is one of the issue. Data transmission, because we have to transmit the data to the cloud and then process the AI machine learning algorithm and get the data and then control it. So there's a time lag between all this process. We have to also solve this issue. But I think it's doable. I think in the future that we can create the entire solution, and then one day that we can realize the Industry 4.0 concept. Okay. Thank you very much. This is all I have today. And do you guys have any questions now?
Thank you, Dr. Yoon, for sharing your valuable opinions, finding, and knowledge with us today. So now session is open for questions and answers.
Dr. Yoon, this is Mike Tastani. Thank you for that presentation. Can I ask you a quick question?
Sure.
The control between the stencil printer and AOI, is that a closed loop feedback, or is there a decision maker in the loop?
So AOI versus the leaf-flow or the mounter, I mean.
Versus the stencil printer, so between the...
printer to the AOI or the printer to the SPI? I'm sorry about that. Yeah.
Is the SPI the AOI?
Yes,
that
that one's
yeah.
Right. Printer to the SPI machine. The company that we are working on, they're already communicating with the kind of the top 3 printing company. So we are actually funded by the inspection company. They already create the machine to machine communication. So it's a closed loop control. But if I just tell you a little bit more about this one, there is no industry standard. So this inspection company has to create a new protocol whenever they get to use the different printer. So let's say that is one printer. If you want to use it, you have to use the certain type of protocol, communication protocol. If you're using ECRA, if you're using Panasonic and other printer, so individually they have to create their new communication protocol. I believe the industry has to come up with the standard way of communicating the data in the future. That's what I'm thinking.
Okay. All right. Thank you for the answer. Thanks for the fascinating work. Thank you.
Thank you.
Vince.
Okay.
So participants, if you have any questions, you guys can ask.
This Professor Samwon Yoon?
Yes.
Yes. Thank you so much. It was an excellent presentation. Thank you. My question is a supplement to what Professor Michael Testani asked. And you mentioned about the lack of industry standards. But isn't that a problem everywhere in every industry today? As more and more automation happens, you find that every manufacturer, every vendor has their own proprietary technology, and the protocols are proprietary. So the connectivity becomes a major problem.
Yes, true. Yeah, it's not only this industry, but I've seen the real cases. I believe when we talk about the connectivity, the company do not have to make a changes on or rebuild their, the intellectual property related data from the machine. I think the main thing is that as a start point, and they need to get an idea like how to share data. So that's kind of the one step. And another way that the people are using it, people are thinking about developing some kind of middleware. So I don't want to let others know that how I'm communicating, but if there's some kind of middleware, and everybody just communicating with the middleware, and then through the middleware, and then we can do certain things. I think that's a sort of direction there. Everybody has to work on it. But by the way, I'm not researching in the middleware and connectivity, but I'm more kind of the solution guy and developing the control solution. So, but this is something that it needed. So it takes time. When companies are trying to, by the way, our solution, some of our solutions are already implemented, and when they get to the implementation, that takes time because of the connectivity issue that they have to deal with. Yeah, thank you for the question.
Thank you.
Sir, I
Okay.
received one question from the participant side. Apart from machine learning, what type of other popular technique of artificial intelligence can be used for the digital transformation for smoothing the functions?
Okay. I'm not sure if I understand the question. Apart from the AI, what type of AI machine learning algorithm that we have to use it? So my opinion is this one. AI machine learning algorithm works well, but it takes time. So what we do is we are combining the traditional solution. So if you look at the quality control or the statistical solution, it still works very well. It's fast. And then combining that method with the AI machine learning method, because the time is issue. If you're looking at the printer cycle, it's about 15 seconds. So within 15 seconds, we need to get the result and then make a changes. Let's say we save the 5 seconds for the changes, like a parameter changes and whatnot. We only have a 10 seconds to process the data and get the algorithm done, and then send the signal. So timing is issue. So what we do is we are combining traditional, like a traditional method with AI method together. And also there's also the short-term solution and long-term solution. In the backbone, AI machine learning algorithm is to keep on running and collecting the data. And also today may be different from tomorrow. Even though we collect the data today, that data may not be useful for the tomorrow. But what about the week after? What about the months after? So there's a lot of issue on that one. So my personal opinion, maybe like some people like who are truly into the AI machine learning will hate me, but I think we have to combine the classical method with the recent technology together. Interestingly, I have done some big data analysis, a big data result, like millions of record. Interestingly, traditional method works better than advanced method. That's what I'm seeing. Okay, I hope that this answer the questions. Okay.
Yeah, thank you, sir. So now I would like to ask another question to you. How
Sure.
is artificial intelligence used to improve usability of systems?
Okay. Artificial intelligence and machine learning algorithm may not be able to improve the usability. I think this is another layer that we have to have it. When we are generating this solution, the company that we are working with, when they're implementing, they have to communicate with a technician. Those technicians do not have AI machine learning knowledge. So if we are using our own language, they cannot understand. So we were asked to provide the result in the graphical user interface, and then some graph or some kind of simple number. That one is a little bit different from the AI machine learning, but this is very, very needed because if people cannot understand the result, they cannot react. So I believe that this is another important question.
Okay, thank you, sir, for your answer. I received another question from the participant side, and he asked that what are the security measures need to be taken care in artificial intelligence?
Okay, another very good question. Very good question. So cyber security is always an issue, but if you're looking at the intranet, so we're working on, right now we are working on the machine-to-machine communication. Data never come out outside of that machine-to-machine communication. So it's a relatively secure. And if you're looking at the smart manufacturing, if all the data is stay in the same factory, and probably it's a relatively secure. But when we talk about the cloud system, and then there's a lot of place that the data can be hijacked. So again, I'm not in the cybersecurity researcher, but I think cybersecurity domain will play the significant role in the future of the Industry 4.0 implementation.
Okay, thank you, sir. Now, I received another question from the participant. And the question is that in AI-based fault classification, how can I justify the use of a feature extraction method and feature selection method over another?
Okay. That's good one. Feature selection and feature extraction is very much needed in this one because of the timing. Because if we are capturing a lot of features and attribute into the AI and machine learning algorithm, the runtime gets longer. So feature extraction and then selection method has to be used, and we are using it. If you see some of my slide, I already mentioned about the feature selection and extraction method. But the question is which extraction, whether we have to use a selection or the extraction, or what sort of the selection and extraction method that we have to use it. Currently, I do not have a good answer for that because we are testing so many different options, and then we are using the best option that we can get based on the experiments. So that's what we are doing it.
Okay, so thank you, sir. Now we can take one more question from the participant side. What is the importance of STM model used for one of the process residue buildup prediction model? And what was the size of data for this process?
Okay, I cannot remember the exact size of the data. So probably it's not hundreds of the PCB board data that we collect, but within one PCB board, and there are multiple apertures. So when we collect the one PCB board data, and then we can actually easily collect the hundreds of the aperture and residual information. So we are using, I think, enough size of the data, I would say. And building a residual model, and we actually tried many different methods. I believe the long-term and short-term memory concept method that we used, and then that result was actually better than the other method. Speaking, if you some of the participant has a question about the algorithm and methodology, I'm coming into this kind of the question these days. A lot of time the random forest method and gets a better result than a lot of the advanced techniques. And I'm not sure whether this entire process a lot of uncertainty. That's why the random forest method gets a better result, because typically random forest method give us actually the baseline. So I have a very the research topic that I want to actually look into it when I get more time. So why those are uncertain or very noisy data when we are dealing with this kind of data, and certain type of method will work better than the other. But if you're looking at the image processing or not, this data is less uncertain or less random data compared to the manufacturing data we are dealing with. So we have to actually find out the right method to use it. So typically we are using a lot of the boosting method and many different methods, and then try to come up with the best solution that we can apply. Okay.
Okay, thank you so much for your answer, sir. So participants, if you have any other question, you guys can ask.
I think somebody has raised his hand. Can that person unmute?
Hello?
Vaibhav, sir, kindly unmute him.
Somebody who just had a number.
Yeah.
There is no one here, actually.
Vaibhav, sir.
Yes, ma'am. There is one question from the participant. Just a moment.
I think this we can keep as the final question, Kriti.
Yes, sir. This will be our last question for today's session. After that, we will proceed further.
There is no any question, ma'am. Sorry.
Okay.
Yeah.
Okay. So I think so, sir. We are done with the question and answer session. And thank you once again, Dr. Yoon, for sharing your opinions today with us. So, and thank you everyone for asking these wonderful questions from your side. So, as Carl Sagan rightly said, imagination will often carry us to worlds that never were, but without it, we go nowhere. So now with this thought, I would like to invite Dr. Amrish Bhatgujjar, Head School of Engineering and Technology, Navrashna University, for the concluding remarks.
Thank you, Professor Kriti. Thank you, Dr. Sangwon Yoon, for sparing your valuable time with us and delivering a wonderful talk on the digital transformation and the role of AI and machine learning in the manufacturing industry. I'm sure that all the participants have received some important information from this particular talk, and they might be interested in associating with you. So they may contact you soon and will come up with few more questions. The kind of questions they have asked, it also shows that the talk has been received very well. So thank you once again for sparing your valuable time with us and enlightening all the participants with the kind of research work that is being carried out at Binghamton University under your guidance. Thank you very much. And I also thank Dean Srihari and Provost Dr. Neela Yagnik for supporting this in Navratna Binghamton University seminar series. And with this, I also thank Professor Michael Testani, Professor Kriti, Professor Vaibhav, Professor Dinesh Panchal for supporting and coordinating this particular event. Last but not the least, I thank all the participants for sparing their valuable time and attending this seminar series. Day by day, this particular seminar series is gaining popularity, and that number of registration that we are receiving each time are growing in numbers. This time we have got more than 350 registration for this particular talk. It shows that this series is received very well by all the participants in India and abroad. So thank you all the participants for attending this seminar, today's seminar. And our next seminar is on 4th June, and that is on Introduction to Neuromarketing. And that will be delivered by Professor Dhaval Mehta of Navratna University. So hope to see you again on that particular seminar on 4th June. Thank you once again. Thank you all for being here, and special thanks to Professor Sangwon Yoon. Thank you for sharing your research. Thank you.
Thank you everyone for joining us today. We will connect in future too. Thanks a lot.
Thank you, Professor Sangwon Yoon, and thank you, Professor Michael Testani. Thanks to all the participants today. Thank you.
Thank you, Provost.
Thank you.
Bish, Kriti, Dinesh, Vaibhav, thank you all. Thank you, Sangwon. Wonderful, wonderful talk. Fascinating research. Keep it going.
Thank you. Thank you, everybody.
Thank you, everyone. Stay safe. Be well.
Okay.
Good day.
Bye now.
Yeah. Good day, sir.
Bye.
Bye.
Bye, sir. Thank you so much.
Kriti and Vaibhav, I'm stopping the live streaming. Huh?
Okay, sir.
Okay. Sure, sir.
Sure, sir. And ma'am, I will soon share all the pics to you. Kriti, ma'am.
Okay, sure, sir. Actually, sir, I think during the meeting, some of the participants have raised for the question and answer, and they were unable to mute himself or herself, right? Now,
We'll take care.
and yeah,
So if
because
we,
I received some queries from their side
Yeah.
that they were unable to mute.
Let them mail their query to maybe Dr. Amrish, and Dr. Amrish can send it to
Professor Mike, yes.
Sangwon. Yeah.
Okay, sure, sir.
You
I
can
will
share
take their
Dr. Amrish,
Yes.
please mail ID with all.